Okay, this is an equilibrium question dealing with a KC calculation predominantly. There are multiple stages to it. I recommend you pause on each section, try to answer it, and then review your answers by following the remainder of the video through. Here's part A, part B, part C, and part D, taking us to a total of 13 marks. So let's look at the answer to part A to begin with. We've been given a huge amount of information here, and you need to be quite systematic in routing through to see what you have and how you can use it. I'm going to recommend you draw out the table, initial moles and equilibrium moles. We can immediately fill two of those in because we were given the actual moles of B and C at the beginning. We weren't given A, but we were given a volume and concentration. So we can use N equals CV to calculate that value, and it goes in. And D will be 0 because we weren't told we had any, and it's a product. Now, I've also been given the equilibrium moles of A. So I now know what the change in A has been. It's gone down by 2.5 by 10 to the minus 3 moles. I can now use the mole ratios to determine what happens in the rest of the cases. Let's take D as the first example. 2 moles of A make 1 mole of D. So 2.5 by 10 to the minus 3 moles will make 1.25 by 10 to the minus 3. So I can put that figure straight in. If I compare A to B, it's a 2 to 1 ratio. So if I've used 2.5 by 10 to the minus 3 moles of A, I've used 1.25 by 10 to the minus 3 moles of B. I started with 9.5 by 10 to the minus 3, I subtract my 1.25 by 10 to the minus 3, and I have 8.25 by 10 to the minus 3 moles. Now when we consider A to C, it's a 2 to 3 ratio. So if I've used 2.5 by 10 to the minus 3 moles of A, I'm going to make 3.75 by 10 to the minus 3 moles of C. If I add my 3.75 by 10 to the minus 3 to the 2.8 by 10 to the minus 2, I end up with 3.175 by 10 to the minus 2. And I've now got my figures that I can add in. You'll notice with C, I've taken it down to 3 significant figures, so there's parity with the remainder. If I move on to B, the expression for KC, well, it's product over reactance. We use the balancing of the equation to determine what powers go in. So this is what we're looking for. C to the power of 3 multiplied by D over A squared times B. In terms of the units, I'm going to use a very old school unit here. We don't use them anymore. But just for simplification, my mole dm to the minus 3, I'm going to put down as a capital M. Because what I can then see is I've got mole dm to the 3 to the power of 4 on the top line and mole dm to the minus 3 to the power of 3 on the bottom line. I can cancel out lots of those and I'm left with mole dm to the minus 3. Moving on to part C, we have got a different equilibrium mixture, so we are going to have to go through the calculation here. Once again, we need our expression for Kc. C cubed times D over A squared times B. Now, I've been given the volume in cm cubed. I'm going to need to convert that to decimeters cubed because I'm going to need to include volume in each of these square brackets because I've been given mole values. So 5 by 10 to the 2 cm cubed is 0.5 dm cubed. At that point, I can put all of my figures in, and you can see the 1.05 moles of B divided by the volume 0.5 to the power of 3, etc. I don't know what my number of moles of A is, so I can't work out the concentration. But what I can do is recognise that this is equal to 116. Rearrangement will find the number of moles. You don't actually need to do x over 0.5. If you leave it as x, it goes straight to the concentration, but you will end up with 0.17 mol dm to the minus 3. Finally, part D, justify the statement that adding more water to the equilibrium mixture in part C will lower the amount of A in the mixture. Well, mark number 1, the concentration will decrease. We know when we add water we're diluting. For the second mark, the equilibrium will move to the side with more moles. In this case, that's to the left. And that is to oppose the decrease in concentration.